All right, hello everyone. So this week we're going to be talking about derivatives. Um, and actually I think this is sort of nice now because for the past couple weeks when we've been talking about limits and we've been talking about continuity, um, really sort of had to redo some stuff in fairly significant ways sometimes to deal with, sort of weird domains, right? What happens if my domain isn't just an interval, right? So I had to change all these definitions to account for potentially accumulation points in my domain and all these sorts of things. But this week we're really going to see that kind of not a lot changes when we go to talk about derivatives. So, a lot of this may be similar to what you've seen maybe in a calculus course or even in a previous analysis course. So we're actually probably this week, like I'm going to go very quickly through some stuff because you'll see that it's not going to have changed at all from really what we were talking about on intervals, except ever so slightly maybe in a definition. But then we'll spend some time sort of going deeper into a couple of different areas. So I've already written up here. So this is, if you're looking in the book, this is definition 2.7. So it's the definition of the derivative. If you just sort of glance at it, right, it almost looks exactly like the definition of a derivative that we used in chapter 1, and it looks almost exactly like the definition of a derivative you likely saw in calculus. So it's worth pointing out though, right, like because we changed some of these earlier definitions and I'm going to be looking at some sort of limit, right? I need this point. I can only define a derivative at an accumulation point, okay? So if A is a point in the domain of my function and it's an accumulation point, then I can define the derivative in exactly the same way I did in calculus 1, right? So I have sort of this limit definition of the derivative, or really I have sort of these two equivalent limit definitions for the derivative here. And if this limit exists, then we say, okay, then that's the derivative of f at a. If it doesn't exist, then we say the function just simply is not differentiable at a. So you can notice already, right? If I have a function, or sorry, if I have a point in my domain which is not an accumulation point of the domain, my function is not differentiable there, right? That follows just sort of immediately from the definition. And of course, sort of the reason that has to be is that this limit won't make any sense if I'm at an accumulation, or sorry, if I'm not at an accumulation point of the domain. All right, perfect. So now what we really want to focus on then is, okay, great. If I have a differentiable function or if I know something about the derivative, sort of what more can I do? And the first sort of very quick theorem that we get here is if f is differentiable, and I'll probably often just abbreviate differentiable in that way. So if f is differentiable at a, then f is continuous at a. Okay. Now this implication only goes one way, right? If f is differentiable at a, then f is continuous at a. But just because the function is continuous at a does not necessarily imply that the function is differentiable at that point. So how do we prove this? Well, my goal is to conclude that my function is continuous. Remember, in our definition of continuity, there were sort of two different things. One, if a was an accumulation point of the domain, and the other, if a was an isolated point of the domain. Well, if I look at this, f is differentiable. Since f is differentiable, that automatically tells me that this is an accumulation point of the domain. So I know A is an accumulation point of the domain, and now I want to show that it's continuous there. So for an accumulation point of the domain, I show it's continuous by showing that we want to show that the limit as x approaches a of f of x is equal to f of a. So that's what we want to show. Equivalently, let me change this ever so slightly. I want to show that the limit of this thing is equal to 0, right? It's really the same thing, okay? So how do I do this? So consider then the limit as x approaches a of f of x minus f of a. Well, this is equal to the limit as x approaches a of f of x minus f of a over x minus a times x minus a, right? Now, so there is sort of some details to be checked. You might complain that these two functions actually are not equal to each other, because this, if I look at this as a function, this is defined at a this function has value 0. This is not defined at a because I have an x minus a in the denominator here. But that's okay, right? Because our limit definition says we're really looking at, right, we're only sort of considering 0 less than absolute value of x minus a less than w. So I'm not actually looking at a. So for every value except for a, these two things are equivalent. So I'm okay there. Okay. Now, if I look at this, I can break this up. Okay, into these two pieces. Okay, and so why am I allowed to sort of make this step? Well, as long as I know that this limit, as long as I know that each of these limit exists, then I'm allowed to do this. And I know that this limit exists because this is by definition just the derivative. So this is f prime of a. This limit exists, it's just 0. And so I get that this whole limit is equal to 0, which is exactly what I wanted to show here, because now I have the limit as x approaches a of f of x is equal to f of a. So this is continuous. All right, great. Again, the converse of this is not true, right? You like taking out the absolute value function, for example. So absolute value of x is continuous at 0, but it's not differentiable at 0. Okay. All right, very good. So the next sort of piece, right, would be to consider sort of thinking about algebra of derivatives. And for a lot of these, I've sort of punted them a little bit and said, well, this really follows sort of from the fact that we have a theorem about algebra of limits. And it is true here that you need to use theorems about algebra of limits here. But to prove these things, you also kind of need to do some creative manipulation of things from time to time. So I'm not going to go through all of these because I think you know the statements of these things. I don't think it's, you can pull a constant outside of a derivative. You know that the derivative of a sum is the sum of the derivatives. You know the product rule, you know the quotient rule, and you can review all those in theorem 2.24. But it's worth noting, and so I just wanted to point out here that if you go and look at, look carefully at the proof that they give in the book. So they prove, for example, the product rule. And so it's worth looking there and seeing that, yes, you use sort of some product rules for limits, but you're also doing a lot of sort of algebraic manipulation of the function you're taking the limit of. So it's not quite as straightforward as some of the other pieces, although the proofs of pulling out a constant are essentially just the fact that you can pull a constant outside a limit. Okay. The other sort of big rule that we will take a look at, though, is the chain rule, and look at its proof. So let's carefully write out the chain rule. So let f from A to B and G from B into R, period. Suppose f is differentiable at x is equal to a, which we're going to assume is some point in the set capital A, and that g is differentiable at b, where b is just the point f of a, and this is in the set capital B. All right, then the chain rule says that the function, sorry, not f composed with g here, this is g composed with f, is differentiable at a, and it will actually tell us what the derivative is. So the derivative of g composed with f at a will be the derivative of f, or sorry, the derivative of g evaluated at f of a times f prime of a. Okay. So again, this is sort of the chain rule you should be familiar with from Calculus 1. We want to look at this sort of carefully, though, and make sure we can prove this. And to do this, we're first going to, this is maybe going to be sort of a theme for today, where we're going to be sort of defining other functions that are going to help us out a little bit later on, although they'll help us out in sort of different ways in each proof. So I'm going to define two functions, u of x and v of t. Okay. And this function u of x is just going to be f of x minus f of a over x minus a minus f prime of a. And this function v of t is going to be g of t minus g of b over t minus b minus g prime of b. Okay, so these points a and b are sort of these points in my theorem here. Okay, so a is just some point in in the domain of the function f, and b is just f of a, and that's living somewhere in the space b. Okay, now what are these functions? So really, they're sort of measuring, right, at a particular x value. If I look at the slope of the tangent line between x and a, how far off is that from the derivative value, right? So one thing we can note is if I look at the limit as x approaches a of u of x, that's going to be 0. Why? Because if I take the limit as x approaches a, this whole term goes to f prime of a. So I just get f prime of a minus f prime of a, which is 0. And similarly, the limit as t approaches b of v of t is equal to 0. Okay, for the same reason. As t goes to b, this function approaches g prime of b. G prime of b minus g prime of b is 0. Okay, so if you're following along sort of in the book, this is, these functions aren't kind of defined quite as explicitly, nor is it quite as much explained why they have these limiting properties, but these are really the same functions, u of x and v of t, that are defined in your book. I'll note that at the bottom of page 63, there is a typo. So if you look there, they have a u of t, and that should be a u of x. So just be careful there. All right, so great. So let me do a little algebraic manipulation here. I don't need a line there. So let me take these sort of first defining equations here. And what I'm going to do is I'm going to solve the first one for the quantity f of x minus f of a, and I'm going to solve the second one for the quantity g of t minus g of b. All right, so f of x minus f of a, if I'm looking at this, it's going to be x minus a times f prime of a plus u of x, and then g of t minus g of b is going to be equal to t minus b times g prime of b plus v of t. So that's just doing some algebraic manipulation here. Okay. All right, but let's see, what else do I know? I know that I'm really thinking of this thing t, right, as being not just any t. So let me let t be equal to f of x. So now I'm defining an explicit relationship between this, between the t and x. So if I do that, then what do I get here? I get g of f of x minus g of b. But what is b? B is just f of a. This is equal to t is f of x minus f of a, and then times g prime of f of a plus v of t. I'm running out of room down there a little bit. Okay. Oh, sorry. And I put plus v of t, but t is f of x. All right. So let me maybe, we're almost to what we want. But let me write this out a little more carefully. Let me just repeat this. So I've got g of f of x minus g of f of a, and hopefully you're starting to see sort of the pieces of the chain rule come together here in this. This is equal to f of x minus f of a, and this is g prime of f of x plus v of f of x. All right, so there's what I have then. Okay. Sorry, there's just some algebra. I have to make sure I do the algebra correctly here. Now I have this f of x minus f of a. I can use this piece here to substitute in for that. So I actually get that this is equal to, so this f of x minus f of a becomes x minus a times f prime of a plus u of x. Well, brackets on there. And then I'm still left with this g prime of f of x plus v of f of x. All right, a lot of algebra here. I think we've reached sort of the peak of the badness, and now things should be getting better. So if x is not equal to a, which again, eventually we're going to take a limit, and we don't really care about what happens when x is equal to a for the limit. So if x is not equal to a, then I can divide both sides by x minus a. Not equal to a, then g of f of x minus g of f of a over x minus a will be equal to, well, that's just going to cancel this here. And so I'll get f prime of a plus u of x times g prime of f of x plus v of f of x. All right, great. Now, I'm now going to take a limit of both sides as x goes to a. Okay, And so what happens, if I now take a limit of both sides as x goes to a, well, on the left-hand side, I'm just going to have the limit as x approaches a of g of f of x minus g of f of a over x minus a, which, if this limit exists, is precisely the definition of g composed with f prime at a. All right, now what about the right-hand side? So as x approaches a, well, this is just a constant with respect to x, and as x approaches a, this goes to 0. That's going to go to 0 in the limit. As x approaches a, okay, well, what's going to happen here? Well, I'm not so sure yet. Let's look at this. So you can see sort of these first terms are easier, but the second terms are a little bit trickier. Now, let me sort of leave this alone for a second and look at this first. As x goes to a, f of x is going to go to f of a. Now, how do I know that? Well, my function f was differentiable at a, which means it's continuous at a. And if it's continuous at a, then as x goes to a, f of x will go to f of a, okay? But that's the same as saying, so x going to a gives me that f of x is going to f of a, but f of x was what I called t, and f of a is what I called b. So really what I have is I have v of t, where t is going to b. But that limit is also 0. So this piece goes to 0 here. Okay. Now I sort of need to justify. Oh, wait, hold on. Actually, maybe I've just carried something over wrong. This should have been g prime of b, which was f of a. Sorry, this, yeah, we shouldn't need to deal with the limit here. F of a, there we go. And that's just a constant, right, as far as the limit is concerned. So what I'm left with is f prime of a times g prime of f of a. Okay. So in fact, I mean, we should be a little careful here when we're justifying this. If I take a limit of both sides, this limit exists, okay, and is equal to this. That means the limit of this whole thing is equal to this, and therefore the derivative, the function is differentiable at a, and its derivative is given by this. Okay. So there's some work there, right? I mean, this is not straightforward, but with sort of using these sort of auxiliary functions u and v, we can kind of make this work. And this is not an uncommon sort of trick for differentiable things, is to sort of look at this difference here. And we'll actually see how these sort of come back when we talk about Taylor's theorem. I guess it'll be a couple of weeks because we'll have the midterm, but we'll see how these sort of things come into play in other situations. Okay. So this is great. You know, this allows us to do some sort of really nice things. One of which I'm not going to go into sort of the full details of, but if you look, the next sort of thing mentioned in your book is sort of the inverse function theorem. And I think I might have you on the exercise set justify some of these pieces. But you can imagine now, right, if I have a function f, which is invertible, and let's say it's an invertible function which is continuous, and it has continuous inverse. Sorry, it's differentiable, and it has differentiable inverse. Then I can actually use the chain rule in a clever way. So I know if I have a function and its inverse, and let's assume all these things are nice and differentiable, then this holds, right? And so I can, this is just f composed with f inverse. And so I can differentiate this. This will be f prime of f inverse of x times f inverse prime of x And then if I differentiate this side with respect to x, that's just 1. And so this gives me a very nice formula for the derivative of the inverse function. Okay, and all I really did was use the chain rule. Now, sort of the trick really in the inverse function theorem, so this is, if you look at theorem 2.6, this is essentially the last of 4 things it says are true. The really tricky details are actually kind of in the first 3. So you'll see that the assumption is that f prime of x is not equal to 0 for every x in some closed interval. And so you need to use all of that to show that f is 1 to 1, that the differentiability of the function implies that the inverse is both continuous and differentiable on a certain set. So there's some details that have to be carefully checked there. And I might walk you through a couple of them in the exercise set. So it's not trivial. Doesn't immediately follow from the chain rule, but sort of this last piece that gives you the equation. I mean, if you have everything sort of, and you know it's well defined and continuous and all this stuff, then that last piece is really just an application of the chain rule. All right. Just like when we talked about derivatives before, one of the big pieces, and one of the pieces to me that is maybe the most useful about differentiation is to talk about sort of mean value theorems. Okay. So we want to look at sort of a few mean value theorems. And you might sort of be thinking, well, there was one mean value theorem, but if you actually think back, right, we looked at mean value theorems for derivatives and for integral sort of expressions, and they're all sort of related, but we'll sort of see how these carry through. But even with just derivatives, right, we started last time with just Rolle's theorem, okay? And so let's sort of remind ourselves, and it's sort of restated here. So suppose f is a function from the closed interval AB into R. So suppose this function satisfies the additional properties that 1, it's continuous on the closed interval AB, it's differentiable on the open interval AB, and for Rolle's theorem, we want the function value at the endpoints to both be the same. Then there exists some C in the interval, in the open interval AB, such that f prime of C is equal to 0. Right. So I think we proved this sort of thing last time. Again, I mean, what's sort of changed from before, maybe there's sort of a bit about continuity and differentiability that's changed because we've defined these things in terms of accumulation points or not. If all these hypotheses are satisfied, if it's differentiable in the open interval AB, well, I should say, actually, this function we're looking at is defined on a closed interval AB. So there's sort of no domain weirdness that you might worry about where you have isolated points and accumulation points of the domain. I mean, every point here is an accumulation point of the domain. The domain is a closed set, right? So there's sort of those weird things you might worry about where we saw weird limit examples or things like that. Those aren't really going to happen here because of the setup. What I want to focus on, though, again, it goes back to this sort of idea that sometimes we can define other functions to really help us out to prove some other things. So this is often in calculus, right? This was referred to as Rolle's theorem. Then you often in calculus talked about the mean value theorem, but there are lots of mean value theorems. So this one is really due to Lagrange. So Lagrange's mean value theorem. And so again, this is the one you're sort of used to. So suppose f from the closed interval AB into R is continuous on the closed interval AB and differentiable on the open interval AB. And now, since it's the regular mean value theorem, I don't need sort of this third part. Then there exists C in the interval AB such that f prime of C is equal to f of B minus f of A over B minus A. All right, so again, nothing surprising here, but let's actually look at the proof here. In some sense, right, you really want to think of this as Rolle's theorem said that your endpoints A and B had to be at the same height, and then you'd get some point in between, at least one point where the derivative was 0. Really what you're thinking about, we're sort of getting rid of these conditions here, so you could sort of be tilting your function in some way. And so really, we're just sort of going to figure out how do we algebraically allow our function to sort of, well, now we're dealing with potentially a tilted function. How do we sort of untilt it to apply Rolle's theorem and then tilt it back to get the result that we want? So let's look at the proof of Lagrange's mean value theorem. And again, I think this is one of these proofs that when you see it, you go, oh, that's super easy. But the hard part is I'm going to say, let me define this random function phi, and then look, it does exactly what we want. And of course, the question is, how would we have ever come up with phi, right? Okay. So here's the proof. So let phi of x be the function f of x minus f of a minus f of b minus f of a over b minus a times x minus a. Okay. So what I'm going to show is that I can actually apply Rolle's theorem to this function phi of x. So note that, okay, a couple of things. First, phi is continuous. Now, why is phi continuous? Well, let's look at all the functions of x that appear in here. So f of x, by assumption, is a continuous function on the closed interval AB. X is a continuous function on the closed interval AB. Everything else is constants. Okay, so phi is continuous on the closed interval AB. Similarly, phi is differentiable on the open interval AB. Now this goes back to all those sort of algebra of differentiability pieces, but f is differentiable, x is differentiable, all the rest of this stuff is constants, so everything is going to be nice and differentiable here. Okay, so this is differentiable. And now finally, and this is sort of, where really why we chose a specific definition of phi comes into play. All right, let's see, what's phi of a? Phi of a, well, that'll be f of a minus f of a, so that'll be 0. And if x is a, then that'll be 0, so that'll be equal to 0. What about phi of b? So this is a slightly trickier one. So let's see, phi of b will be f of b minus f of a minus f of b minus f of a over b minus a times, I'm plugging in b here, so b minus a. Then I have f of b minus f of a minus f of b minus f of a. That'll be 0. So essentially, if you ask me sort of why I chose this function, I would say because this is the function that takes sort of, here's f of a, and here's f of b, right? And it takes and it maps these two endpoints down to 0. Okay? So this is exactly the function that will take my endpoints and map them down to 0. And in fact, it's really just a linear function. Well, sorry, I shouldn't quite say that. It's not exactly a linear function. But it does this sort of in exactly the way I want. Okay. All right. So now what can I do? So then by Rolle's theorem, there exists some C in AB such that f prime of C is equal to 0. Or sorry, phi prime of C is equal to 0. But let's see, what is phi prime? Phi prime of x, let's see, derivative of this thing will just be f prime of x. And derivative of this thing will be, well, this is just x times this, so it'll be f of b minus f of a over b minus a. Okay, so where phi prime of c is equal to 0, I'll get that this is equal to 0. And now if I look at this, this is just saying that f prime of c then is f of b minus f of a over b minus a. So earlier when I said I'm choosing this phi, not only so it maps these endpoints down, but also so that phi prime of c will end up working here. Okay. So again, this is a proof that I think when you see it, it doesn't convey the historical sort of discovery of these things, right? Somebody didn't just know to try this definition of phi, right? It was sort of cooked up so that it would work out in this proof, right? But there were many sort of different versions of this proof or different ways of thinking about this before somebody found, oh, just define this function phi, you can apply Rolle's theorem and be done. So that's sort of one way of doing that. There's yet another version of the mean value theorem, Cauchy's mean value theorem, which is theorem 231. I'm going to have you write out sort of the details of that. If you look at the proof, it says, here's some auxiliary function and apply Rolle's theorem. Well, okay, there's a little bit of work to be done, right? As I did here to show, right? And right, you would need to write out and explain, how do you know it's continuous? How do you know it's differentiable? How do you know that in this case, this function psi, how do you know psi of A is equal to psi of B? But they give you the auxiliary function, so you should be able to sort of work through those details. All right. So we're going to stop the recording there for today. And next time we'll come back and we'll start looking at L'Hopital's rule, and then we'll move on into sort of higher derivatives, and in particular, really with an eye towards Taylor's theorem, and then moving into talking about integration.